Let's get started. So today is the last lecture for the data science series, and then 2 days from now we will start with the machine learning series. So today's topic is basic probability and statistics. So Parth, Sudhakar, and couple of others, they have helped me prepare this topic. So we'll first go through some basic concepts. I hope you already got some of the pre-read material, and then we will go into how to implement some of these concepts using Python. Uh, so let's get started. So the learning objectives are basically what you should be able to do is basically match the probability density functions and probability mass functions to outcomes of random experiments. You should be able to write the relationship between a PDF and a CDF. You should be able to list some common distributions and their parameters, means and variances, and write the conditions for statistical independence of two variables, and also the equation for likelihood of a parametric distribution, and then write down the steps for hypothesis testing. Right. So let's move. So the central concept to probability and statistics is that of a random variable. So random variables can be discrete or continuous. So discrete means they will take only fixed values such as 0, 1 or 0, 1, 2, 3, 4, 5. And continuous means they can take any value between, on the entire real line. So the example of a discrete outcome is a coin toss. So if you toss a coin, you can get head or tail, but it doesn't become a random variable unless we map it to something. So for example, let's say we map it to two numbers. So we map it to a variable that can take values either 0 or 1. So let's say 0 for heads and 1 for tails. Okay. So this value can change every time the experiment is conducted. So every time you toss a coin, right? So that is an experiment. So when you toss the coin, you get a value for that variable X, and that value can be either 0 or 1, right? So that value that you get is a sample from the entire population that you can get. So the population is basically only two different outcomes, and from that you can get one sample. Okay. So such a variable is a random variable. What random means is that every time you toss the coin, you cannot predict whether it will give you 0 or 1. So, but it does not mean, randomness does not mean that all outcomes are equiprobable. Please, this is an important concept to note. Some people think that randomness means everything is equally likely. In our life is random in many ways. We may work hard, but we may not get the fruit we desire at some point. Sometimes we may not work hard, but we may get very good outcome. So in that way, it is random, but it doesn't mean that anything can happen to anyone. If you look at statistics of what happened to people, hard workers do get better outcomes on an average, right? So there is something that can be predicted. So here the picture that I have shown is that of a biased coin, right? So if this coin was like a cylinder, very flat cylinder, then the chance of this coin landing on head or landing on tail would be equiprobable. But if it is not a cylinder, if it is a frustum of a cone, then the chance of it landing on head down and tail up is much higher than the other way around, where the tail is down and head is up, right? Not much higher, but let's say slightly higher. So this is not a fair coin, it's a biased coin. So you can predict that most of the times it will show you tails, or more times it will show you tails than heads, right? But it doesn't mean that you can predict every outcome with certainty. Okay, so that's what randomness means. Randomness does not mean equiprobability. Okay. So with that said, now let's look at what, so this would be a discrete random variable. There are continuous random variables. So for example, height of a person is a continuous random variable. So the height may range from, let's say, 0.5 meters to 2.5 meters, right? And so let's say you conduct an experiment that you will close your eyes and you will open your eyes on a busy road, and you will measure the height of the next person that you see. Okay, so that's a random variable now. So that height is a continuous variable, and it's an example of a continuous random variable. Now this is not completely random. You will not see people who are less than 1 foot. Even newborns are more than 1 foot. and you will not see people who are taller than 7 feet or 8 feet. Okay, so there is some predictability, but yet you cannot predict each and every sample from that outcome. So in that way, it is random. Okay. So the probability of a random variable taking a value is what concerns most of statistics and probability, right? So each outcome of an experiment is associated with that probability, and the expected proportion of times that you will see that outcome is the probability. So for example, if you have a fair coin, then your probability of head and probability of tail would be same, which is half, 0.5, right? So all, if you take probabilities of all possible outcomes and you add them up, it should add up to 1. If it is a continuous variable, then you will integrate over the probabilities over all possible outcomes, the entire range of x, and you will get the integral to be 1. So for a biased coin, this may mean that your 0 and 1 are slightly different, have different probabilities. One has 0.53, let's say, and the other has 0.47. So the way we indicate that is a capital variable x, right? So x taking some value 0 would be. Hello, can you please mute yourself? All right, thank you. Yeah, so now let's come to continuous random variables. In continuous random variables, the variable taking a some specific value, that probability is always 0. So let's take the example of a height, right? The probability that the person that you see next has a has the height of 1.6000000 meters exactly is 0, right? So the person might be slightly taller than 1.6, slightly lower than 1.6, much taller than 1.6, much shorter than 1.6 meters, but having exactly 1.6, that probability is 0. So that is the difference between discrete and continuous random variables, which is very important. Continuous random variables, the probability of the variable taking one particular value is 0. Okay. But the probability of an interval is finite. So if I say the probability of someone's height being between 1 meter and 2.5 meters is 66% or 0.66, that is not 0. So that I can define. So that is a finite number. So you have to look at intervals. Continuous random variables always look at intervals, or you look at comparison of two different values. Kasina, what's your question?
Yes, sir. So for a continuous variable, can we say to determine the probabilities? Do we plot a probability distribution function, a PDF?
Yes, we plot a PDF, but don't get too hung up on reading the value of the PDF. Always read the relative value of the PDF, not the absolute value of the PDF.
Okay.
Okay. So you can say that probability of someone being 1.6 meters is more than someone being 1 meter. That you can say, but you cannot say that probability of someone being 1.6 meters is 0.2. That doesn't make sense. It is always 0. Okay. Ashish,
Sir, yeah, this question, the thing that why the probability is equal to 0 is because of the integral, right? Because
it
we
is
cannot
because of
determine integral
the
at a
integral.
certain point. We have to take it in an interval.
Absolutely, absolutely. That is the right answer. Divyansh? Okay. All right. So let's move ahead. So if you look at discrete variables, then you would define the probability. You would map the probability onto a function, which is a probability mass function. So you will have some discrete values, and each discrete value will have a finite probability, unlike a continuous distribution where you don't have finite probabilities. You have finite probability densities, not finite probabilities. Okay, so let's say there is a discrete random variable capital X, and it can take only 3 values, 1, 3, and 7. So their probabilities could be, let's say, 0.2, 0.5, and zero point 0.3, and they all add up to 1. Okay. And for any other value of X, the probability will be 0. Let's see, that looks like there are some chat questions. Is continuous probability used for comparison? So what I mean by comparison is that you can take two values of X, and then you won't say probability, you will say likelihood of X taking a certain value A versus x taking another value b can be compared. Okay, but you cannot, the probability you cannot compare because probability is 0. Okay, so now let's talk about continuous random variables. So in continuous random variables, now let's say there's a variable x which is a continuous random variable. So probability that capital X takes some value small x will be 0 for a continuous random variable, but we can define it for intervals. Now if we take the interval, let's say x1 to x2, can you see my cursor? So if you take the interval x1 to x2 and you integrate this probability density function px dx, right? So that will be the probability that capital X takes the value in that interval from x1 to x2. And if you take the entire real line as the interval minus infinity to plus infinity, then this will all integrate to 1. So the area under the curve is always 1, the PDF curve. So if you have a PDF that doesn't give you, if you have a function that doesn't give you integral 1, usually you normalize it so that it gives you integral 1. So there are many things you can actually easily guess from by looking at this PDF, right? So the maximum value of the PDF, the peak of the PDF is the mode. Okay, that is the most likely value of the random variable capital X. Right? And if you look at the area and you can draw a vertical line such that the left area and the right area from that line are equal, then you have found the median. Okay, so median is the mid value in terms of, if you order all the points in terms of their if you order all the points and you look at the probability, so the probability on the left of the median and right of the median is equal, 0.5. Okay, so minus infinity to median, that integral is 0.5. Median to plus infinity, that integral is also 0.5. And mean is where you can balance the weight of the probability distribution. That means the left side weight and the right side weight is equal. Okay, so it's basically in some sense it is the weighted average of x. It's the probability weighted average of x. Looks like there are some questions. So I'll give you a more formal definition of the means shortly. Manan, what's your question?
Can we comment on the probability of most likely value?
So there is the probability of most likely value is also 0. The likelihood of the most likely value is the highest. Okay, so let's call it likelihood, not probability. Probability of the most likely value is 0. So it's the likelihood that is the highest. Prasoon?
Sir, can you explain the mean from PDF again, please?
Right. So mean I will explain in the next slide, and I will explain only the median. The median here in this slide. So basically, the median means that that the left area and the right area are equal. Both are 0.5. So mean, the reason I will explain in the next slide is basically it is the weighted average of x in some sense, weighted by the probability.
Okay, sir.
So okay, let's take it in the next slide. Ram Mohan.
So what is the intuition behind the mode in a continuous variable, sir? Because in discrete variables, we know the number of frequency is higher. In continuous
Yes. So mode means, yeah. So mode means that if you divide into small intervals, if you divide the entire range of x into small intervals, okay, then the interval that contains the mode will have the highest frequency if you take a lot of samples.
Okay.
Abhilash has a question. I couldn't understand the probability of random variable taking a particular value is 0. We don't take integrals to calculate probability, only cumulative probability, I guess. Yes. So basically, because if you take just one value, then that interval around that value is infinitesimally small. So the area in that interval is infinitesimally small, and that is 0. Okay. All right. Let's move forward. Okay, so cumulative distribution function, like we explained in one of the previous lectures, is basically the cumulative probability until that point x. So let's say I have the probability density function px, and I want to find CDF, okay, the cumulative distribution function. So what I will do is I will integrate from minus infinity to that particular value x1. So that will be basically the PDF, the CDF at x1. Okay. So the area to the left of a point is if I plot that, that is I plot the integral, that basically that becomes the CDF. So the CDF, as you can imagine, starts at 0 at minus infinity, and at plus infinity it becomes 1, because that entire integral is 1 from minus infinity to plus infinity, and it is a non-decreasing function. So if we look at these CDFs, so basically if we look at discrete random variables, then this CDF will be a step function where the step will change every time the discrete value for which there's a finite probability that occurs. So for example, let's say you had three different outcomes for a football match. So let's say you could win, you could draw, or you could lose, right? So win probability for a particular team is 0.7, draw probability is 0.2, and lose probability is 0.1, right? So let's map it to a random variable capital X, which takes three values, 0, 1, and 3. So these are any guesses that these are the points in a football match. So if you win, you get 3 points. If you draw, you get 1 point. If you lose, you get 0 points. Okay. So can we draw the CDF of X? So if you imagine that this CDF would look like a three-step function, then you guessed it right. And that's what we have here, right? So until 0, the CDF is 0. Then it goes up to 0.1 because the probability was 0.1 for a loss. And then for draw, the probability is 0.2, so it jumps up another 0.2 points, so it reaches 0.3. And then the win probability is 0.7, so at 3 it jumps 0.7 up, all reaching all the way to 1. Any questions, Hitesh?
So can you please explain once again the CDF of the same?
Yeah, so if you think about the PDF, what the PDF would look like is at 0, it will have a peak. It will have a peak that will have 0.1. At 1, it will have a peak that will be as high as 0.2. And at 3, it will have a peak that will be as high as 0.7, right? So these are three impulses that are at three different locations. One impulse is at 0, the second impulse is at 1, the third impulse is at 3. Now, if you integrate these three impulses, what you get when you integrate an impulse, you get a finite jump, discontinuous jump. Okay. So
Okay.
that's why you get a step at 0, and then at a step at 1, and then a step at 3. So why it is called
Okay.
cumulative means because it accumulates all the probability to the left hand side. So it is additive, like San has said in the chat. So that's why it is called cumulative. Can we say features used in machine learning is also a random variable? Yes, we can say that. So basically we are building towards those concepts. Let's look at some hands that have been raised. No hands have been raised. Naveen, you have a question? Okay, good. All right, so let's move forward. So properties of CDF, that it ranges from 0 to 1. Okay, it's a non-decreasing function. At minus infinity it is 0, at plus infinity it is 1. Okay. So now let's look at expected value of a random variable, right? So let's say if we are looking at the random variable x, okay, and we have the PDF which is shown in these curves on the right. Okay, so if you think about this PDF curve, right, you divide it into small intervals, infinitesimally small intervals. So the height of each interval is the weight that you associate with that particular value of x in that interval. Okay, so what you are doing here is you are taking a weighted average of some sort of x. So the mean of x, what we call in statistical sense, is the weighted average of x, weighted by the probability density function. In discrete variables, instead of this integral, you will have a sum ranging from minus infinity to plus infinity, and instead of px being the PDF, you will have the px being the probability mass function. That is all that is different. Otherwise both are the same. So you can think of PDFs as infinitesimally small uh, intervals that act like a PMF. Okay, let's look at some questions. Is CDF the double integral of probability function? It's a single integral only. Yes. Uh, all right. Any hands that have been raised? Arindam?
Hello, am I audible?
Yes. Yes.
Sir, actually, I had a question that in CDF we are plotting the integration to a random variable, but is the random variable in that plot continuous? And actually, the random variable is only 1, 2, and 3, right? So my space is 1, 2, and 3 only. So how am I plotting it in a real line?
So here I'm in probability mass functions, we are assuming that it takes only these three values. So by default, its probability of taking any other value is just 0. That's how we are thinking about it.
Oh, okay, okay,
But usually CDFs usually make sense only in continuous variables.
oh, okay, sir, thank you.
Ashish?
Sir, if I tie this concept back to arithmetic mean, right? Like when we take an arithmetic mean, so
Right.
I think there's a hidden assumption over there in the case of arithmetic mean that every, like for example, every number that occurs for which we have, like, for example, there's a list and we have to take a mean of that list. So it means that every element of the list has equal probability of occurring. Now tell me what is the expected value out of it, right?
Absolutely. Yeah. So there it's called a uniform prior or a uniform probability distribution.
Yeah. Thank
So
you, sir.
where all values are equally probable, your distribution function looks like a flat bar. Okay. All right. What are the practical uses of a CDF? So CDF and PDF, I mean, they are interchangeable in terms of practical usage. Uh, One particular usage of CDF is to convert to sample from other distributions. So if you look at random number generators, most of them they generate a random number from a uniform distribution. So if you want to convert uniform distribution to any other distribution, CDF is required. Okay, so expected value of a random variable, like what we mentioned in the previous case, was the weighted integral of x, right? Weighted by its probability. So here, in a discrete way, example that we looked at, where we had three different values, 0, 1, and 3, the expected value would be the weighted average of 0, 1, and 3, where the weights are their probabilities 0 0.1, 0 0.2, and 0.7 respectively. So if you take the weighted average of 0, 1, and 3 with these weights, the answer that you get is 2.3. Okay. So what we saw earlier was the expected value of x, right? So that was basically integral of x weighted by p of x from minus infinity to infinity. We need not just restrict ourselves to computing the weighted value of only x. We can compute the weighted average of any function of x. Okay, so this could be any function like x square, x cube, sine of x, cos of x, whatever it is, some function you can plug in, and what that will do is it will give you the expected value of f of x. What that means is that if I were to draw infinite number of samples of x and compute the values of f of x and take their average, the the value that I'm expected to see is given by this integral. Okay. The notation here is that E means expected value, X means the random variable X. This tilde sign P means X sampled from the probability distribution P. Okay. So expected value of f of X when X is sampled from the probability distribution P. Any questions? Anything in the chat?
Sir, what is the meaning of P in that
P,
equation?
P is the probability density function.
No, no, X tilde P. So in that P is the probability.
P is the probability density function. X tilde P means X was sampled from P.
Okay.
So think about it this way. Assume that the world works a certain way. The world has a particular distribution of X we are sampling from and that distribution is given by p. We are sampling
Okay.
from that distribution. Okay, so that's what it means.
Okay.
So if we sample from that distribution, the expected value of a function of x is given by this integral. Okay, so now we will plug in some values for these functions and see what we get. Okay, so the first thing that we will plug into this function, so let's say y or this function f is x cubed. Okay, so x cubed for 0, 1 and 3 are 0, 1 and 27 respectively. So we have 0, 1 and 27. Okay, and hold on, let me see if I can get my laser pointer. No, I guess I don't have it here. Can you see my cursor?
Yes, sir.
Okay, great. So the cubed values are 0, 1 and 27, and then the probabilities are 0 0.1, 0 0.2 and 0.7. So instead of an integral, we have a sum for a discrete random variable. So now we have a weighted average of 0, 1 and 27, which is 19.1. Okay. Then another quantity that we are interested in other than expected value or the mean value of a function, sorry, mean value of a random variable, is the dispersion. How spread out is that probability distribution? So variance is a measure of dispersion, and what is shown in this figure are basically two different Gaussian distributions. Both of them have a mean of 0. Both are centered at 0, but the pink one is less dispersed, the blue one is more dispersed. Okay, so the pink one has a sigma of 1, whereas the blue one has a sigma of 2. Okay, so although both have the most likely value as 0, if you take an interval of -1 to 1, then if you sample from the pink distribution, you are more likely to get a value between -1 to 1. Whereas if you sample from the blue distribution, you are less likely to get a value between -1 and 1. Okay, let's look at some questions. So CDF is much more convenient than integrating PDF from A to B. In some sense, yes. Okay. Any other questions? Okay, let's move forward. So the variance of a random variable, okay, that would be the expected value of x minus the mean of x, or the expected value of x whole square. Okay, so basically whatever is the expected value, or which we call in other words mean, so we subtract x, the mean, from x, right? So some x would be greater than the mean, some x would be less than the mean. So we don't want all of these to cancel each other. We want to see how much they are spread to the left, how much they are spread to the right combined. So we will take this difference and we'll square it. So we will get a positive function. So this positive function, this is the f of x now. Its expected value when weighted by the probability density function p of x, that is the variance of this variable x, and the standard deviation is the square root of the variance. Okay. Similarly, we can define other central moments. We can take x minus mu x, and then we can take, usually you don't write mu x, you will write x bar. That is the expected value of x. So x minus mu of x, and then you can take it to the power not just 2, you can take it to the power 3 to the power 4. So these are different central moments. So if you take it to the power 3, then it is a measure of skew, whether it is left skewed or right skewed. Okay. So if skew is positive, then a lot of values lie on the right side, away from the right side, further to the right side of the mean. And if they are negative, then they lie to the left side of the mean. And 4 is, if you raise it to the power 4, that's a measure, another measure that's called kurtosis. Okay. So the variance of a random variable, coming back to this, would be x minus mu of x whole squared, the expected value of that. Here we have dropped the notation x sampled from px, that is to be assumed. So if you simplify this formula, what you get is expected value of x square minus the mean squared. So for example, if we go back to the discrete case, where we had three different values, 0, 1 and 3. Okay, so we are taking the expected value of x square, which is 0, 1, and 9. They are weighted sum where the probabilities are the weights, zero point 0.1, 0.2, and zero point 0.7. So that is 6.5. And then we will subtract the mean squared. Mean was 2.3 squared, which is 5.29. So the variance is 1.21, or the standard deviation is square root of 1.21. Questions? What does skew mean physically? Skew means if you take the mean value, does the probability distribution stretch further to the right or further to the left? That's what skew means. Or is it equally stretched to both sides? Kurtosis is, I forgot what it is. It's basically, it's another measure of shape other than, I mean, it's a higher moment than, it's basically how much it adheres to a Gaussian bell curve or not. Whether it is more condensed than a bell curve, or does it have more fatter tails than the bell curve? That's what kurtosis means. All right. So now let's look at some common distributions that you should know about. One of them, the most basic one, is a Bernoulli distribution. This is the distribution that would measure, that would model, not measure, model the random event of a coin toss. So let's say if you had two different outcomes, 0 and 1, okay, then your Bernoulli, you would have a Bernoulli variable which takes a binary value, and what we would define this probability distribution is with a parameter p, small p, and that parameter tells you the probability that this variable will take value 1, and by definition 1 minus p is the probability that it will take the value 0. So now if we look at the expected value of x, right? So before that, let's look at the complete expression for p of x. So here it is important, there's a trick involved here. So the probability function need not be written in this conditional form p and 1 minus p. You can directly write it in a single line by saying that p to the power x 1 minus p to the power 1 minus x. Why? Because x can only take value 0 or 1. If it takes value 0, then p will not matter. The answer will be 1 minus p. If it takes value 1, then 1 minus p will not matter. The answer will be p to the power x. Okay. So the value of this function will be either p or 1 minus p. Now, if you look at the expected value of x, so as you can imagine, that will be p. We can actually mathematically work it out also. So the weighted average of p and 1 minus p, the weighted average of 0 and 1 weighted by p and 1 minus p respectively is p. And the weighted average of the x minus its mean, so would be, so you take 1 and then 1 minus p whole squared, its probability is p, and then you take p squared and its probability is 1 minus p, and then basically what you will get is variance is p times 1 minus p. Any questions? What is the difference between skew and kurtosis? Skew tells you whether, if you look at the mean, whether the distribution is more spread out to the right or to the left. Kurtosis means whether whether the distribution looks more like a Gaussian, or does it have a fatter tail than Gaussian, or thinner tail than Gaussian. What does it physically mean for a random variable having outcome 0 or 1 to have expected value p? So that is basically like a biased coin. Biased coin, its value, expected value will be, uh, if the outcomes are 0 and 1, expected value will be p. That means it will not be, it need not be 0.5, it will be whatever is the bias in the coin. Let's look at if there are any questions in YouTube. Okay, no questions. Okay, the next distribution that you should know very well is binomial distribution. So binomial distribution is a sum of Bernoulli variables. So let's say instead of tossing the coin once, I toss it n different times. Okay, then for one coin toss, let's say the probability of getting 1 is p. Then for n different coin tosses, what is the sum of ones? What is the probability of getting 6 heads when I toss a coin 10 different times. If it is a fair coin, then it will be 0.6. But let's say it is not a fair coin, p is not equal to 0.5, then what is the formula? That works for both 0.5 and other values of p also. So the formula for that is n choose x, p to the power x, 1 minus p to the power n minus x. It will be a good exercise to look at this formula and sum it up from different values of x. The different values of x are 0 to n, and what you will get is when you sum them up, it will all come out to be 1. Okay, which is what it should be. Clear? So similarly, expected value of x would be, this should be capital N times p, which is obvious, right? So if the probability of one heads is p, then the probability of n heads is n times p. Oh, sorry, the expected value of the number of heads you will get when you toss the coin n times would be n times p, right? And the variance, again plugging it into the formula, will be n times p 1 minus p. The most important distribution probably that you will encounter is the Gaussian distribution. Kasina, you have a question?
Yes, sir. So in the binomial distribution, like
Yeah.
sorry, for any distribution, can we say the expected value is for the number of times we are doing the experiment, like the number of times we are doing the experiment, it is the probability of the occurrence of the positive result.
Occurrence of the positive result? No, there is no such thing as positive result. It is just we named something as 1, we mapped something to 1.
Okay.
uh, I don't want
So
to call it positive or negative. Yeah, it's the expected value of that variable. So if I had mapped it to 0 to 2 instead of 2 0 and 2 instead of 0 and 1, then it would be 2 times p or something, right? So
okay,
it's
yeah,
basically how you frame the question, how
got
you
it.
frame the random variable. Yeah. Prasun?
Sir, in the previous slide, that is there is n and x you have written. So is that I couldn't understand that notation. Yeah,
Which one?
px
Oh,
equal
yeah,
to.
that is n. You, yeah, so from 11th 12th class probability, there is a notation called ncx.
Okay, okay,
N choose
ncx.
x.
Okay, ncx, that
Huh.
is okay.
So that is more, yeah, that ncx is more popular in India, in high school in India, but in international literature it is this bracket nx.
Okay. Thank you, sir.
Okay. Okay. So among continuous random variables, one of the most common distributions that is assumed, it may not be in real life, but what is assumed is a Gaussian distribution. And here you will have a continuous random variable x, and what we will say is that it is sampled from capital N with a mu sigma, with a mean of mu and a variance of sigma squared. And the formula for that would be what is written here: f of x is 1 by square root of 2 pi sigma square, and then e to the power minus x minus mu whole squared by 2 sigma squared. If you integrate this function, you should get 1. And if you multiply this function with x and then you integrate it from minus infinity to infinity, what you will get is the expected value, which will be mu. And if you take x minus mu whole squared, multiply it with f of x, and then integrate from minus infinity to infinity, you will get the variance, which should be sigma squared. Okay. So it is and the reason this is important is many random variables in real life are distributed as per something that is very close to a Gaussian, because of something called central limit theorem. So what that means is that if central limit theorem states is that is if you have one experiment that has a particular distribution, but if you have several experiments and they all add up, then they will the the distribution of the addition will start to look like a Gaussian. Normal distribution is a special case of Gaussian. Many people just use it interchangeably, normal and Gaussian. Gaussian is only for continuous random variables, right? It is not for discrete variables. Sir, could you tell me the different, what is the essential meaning of expected value? Yeah, it is like mean. It is basically mean, but it is that mean is not defined for. I mean, it's a technical term for mean, and it works for continuous random variables also. Ashish, what's your question?
Sir, for the definition of the central limit theorem that you mentioned, precise
Hmm.
definition of it, I think, is that if you take a sample, right, and you take infinite such samples, and you take mean and you plot the mean, then it shows a Gaussian distribution, right?
Right,
Like
right,
mean,
right, right.
yeah, but how does it adds to this thing when you call
Yeah.
like additively and all those things, when you just talked about like
So
when you
mean
keep
is
on
nothing
adding a
but
lot of.
addition and then separate. Yeah, right. So mean is nothing but addition and then dividing by a fixed number, right? So both definitions are equivalent. Okay. All right. So these are some different Gaussian distributions that we are showing here. So if you, there's something called a standard normal distribution. The standard normal distribution is the one where the mean is 0 and the standard deviation or the variance is 1. So your mu will be 0 and sigma will be 1, and there will be around this 68.2% probability between plus minus 1 sigma. Okay. And then if you take plus minus 2 sigma, you will have another extra this 27.2% probability will be included in that, and so forth. So but just having a mean of 0 and a sigma of 1 is not very useful. So there are other Gaussian distributions where the mean and sigma will be different. So the effect of changing mean and sigma would be something what is shown on the right. So if you look at the red curve has a mean of 2 and it has a smaller standard deviation, which is zero point 0.5. The blue curve is a standard normal distribution with mean of 0 and standard deviation of 1. Green curve is uh, is basically is a wider Gaussian distribution or wider normal distribution, which has a mean of -2 and a standard deviation of 2. So notice that when standard deviation goes up, the height of the curve goes down because the area has to still integrate to 1. When it becomes narrower, the height goes up. Okay. All right. Another distribution that is quite useful is the exponential distribution. So here the definition of it is that your f of x would be lambda times e to the power minus lambda x. So if you increase lambda, so lambda is greater than 0. Lambda will always be greater than 0. And the distribution would be 0 on the left side of 0. When x is less than 0, f of x will be 0. That means here x can only take positive values. Okay. And what happens with this is that if you increase lambda, the exponential will go down much faster. If you decrease lambda, it will go down much slower. So expected value of x will be inverse of lambda, 1 by lambda, and variance of x would be 1 by lambda square. Okay, so if you increase lambda, your expected value will be closer to 0. If you decrease lambda, then your expected value will be further away to the right from 0. Lambda will be always greater than 0. So here's a pictorial. So you see three different lambdas, 0.5, 1, and 1.5. For 0.5, you can see that the distribution is 0 on the left hand side of 0, but it starts at a lower value around 0.5, and then it goes much further to the right. It has a fatter tail in some sense. But if you look at the purple one, it starts higher, but it dies down quicker. If you look at the blue one, it starts even higher and it dies down much quicker. Let's look at some questions. There are there are two things: number of measurements and number of samples in each measurement. So should how do we play with both this? I didn't understand this question. Amay, do you want to ask that question? What what would be the CDF and PDF of exponential distribution? PDF is what is shown on this picture. If you integrate this, you will get the CDF. Okay. Amir, yeah, ask your question, please.
Hello.
Yes.
Yeah, so there's a question a little while back about like something about the mean. Like you have a few measurements and then you calculate the mean. So what I'd like to
Yeah.
ask is, so if you, so one is if you increase the number of measurements that you do, then
Yeah.
then you'll go in one direction. Or two, if you don't take too many measurements, but for every measurement you have a lot of samples. Like you have a lot of, for every given instance you have lots of data coming in, and then you take the mean from them. So those are two different things, right? Like suppose you
No,
have,
I mean,
huh?
yeah, we usually think of it as just one sample, not like multiple samples for each instance. Sample and instance are usually used interchangeably.
Can
So
I
you
just
either get 10 samples or you get 100 samples. There's no like 10 samples within 10 within 5 instances or
No, no,
something.
I meant like suppose you say you want to say you want to measure the age or something. So you
Yeah.
take samples of length of size 10, and you keep taking, like you take 100 samples of size 10 from
Ah,
different
I see, I
places,
see. So,
or
oh,
you
so,
take
huh.
1,000 samples of size 5. So those will make a difference, right? So
So what you're talking about is, let's say you have 5 marbles and each marble you measure 3 times. So there is some measurement error that is in each of those three
yeah, so
measurements.
will
And
that be
then you also
cancelled
have
by
five marbles.
increasing the number of times we
No,
take it?
no. So those are, yeah. So that's basically you are introducing a random variable within a random variable in some sense.
Okay.
Okay. All right. Okay. Another nice distribution to know is the gamma distribution. The good thing about gamma distribution is basically that it will be, it's not defined for, see, Gaussians, the Gaussian distributions, although they are very useful, uh, some natural phenomena cannot be measured in terms of Gaussian distribution. People think that people's heights are Gaussian distributed, but Gaussian distribution will always have finite likelihood even for negative values. Heights cannot be negative, right? So there are some distributions that help you model that, so that you don't have negative values. Exponential is one of them. The next one is gamma distribution. So I will not go into the details, but this is what it looks like. There are two parameters that control the gamma distribution shape. They are alpha and beta. Here it is k and lambda, which is same as alpha and beta. So if, as you can see, that alpha or k determines the overall shape, whether it is looks like more like a exponential, or does it look more like a Gaussian, or something in between. And lambda tells you how much will it be shifted to the right, or lambda or beta, whatever one of the other parameters will tell you how much it will be stretched to the right. One is shape control, the other is stretch control. So in normal you don't have a shape change, you have a mean change, you have a location change, and you have a stretch change. Okay. uh, let's go to the next one. Okay, now we'll talk about, we'll shift gears and we'll talk about multiple random variables. So let's say one random variable by itself may not be quite useful. So we want to now look at multiple random variables. In machine learning, you will look at lots of random variables together. So here, let's look at first a pair of random variables, x and y. So just like we had p of x, now we will have p of x and y. And it will be basically a surface on the xy plane, and the entire volume under this surface will integrate to 1. Okay, so it will be a double integral on both x and y, and that will basically integrate to 1. So now you can take slices of this two-dimensional surface, you can take projections of these two-dimensional surface, and you can do lots of different things with that. Okay, so it becomes more interesting now. So is this clear? So if you look at this particular, you have the x direction, you have the y direction, which are orthogonal, and the third direction that is coming on top of it, that is the value of the PDF. Manan, what's your question?
Can you explain the figure showed in right and the projection on the base?
Yeah, so let's first look at the figure on the left. If that is clear, then let's look at the one on the right. So what that means is, let's say I have two different values. So let's say I'm looking at height and weight of a person. So one is x, the other is y. Okay. So you think X and Y are correlated, right? Taller people are heavier, right? So there will be some relation between X and Y. These need not be independent variables, but it is also not a complete deterministic relation between X and Y. There's a probabilistic or a stochastic relation. So someone who's around between 6 and 6.1, 6 and 6.1 feet, let's say, their weight will is still not deterministic in the sense that you cannot predict it very accurately, but you can probably have a distribution for people, uh, distribution for the weight of people of a certain height, right? So what is shown on the right is, let's say, if I sample thousands of people and each person becomes a dot in the height space and the weight space, so the dots will look something like this, right? So most of the dots would be concentrated around a center if it is a two-dimensional Gaussian distribution or a two-dimensional unimodal distribution. So most people are around, let's say, 5 foot 6 inches, and they weigh around 70 kilos. Okay, but then there's a spread around it, and that spread is also not it is not like stretched only in the weights direction or only in the height direction. It's actually, there's some correlation that is between the two. So this is like a scatter plot that you can see of these black dots that you see inside that green circle. Okay, so now if you project, basically you draw a line in one direction and count all the number of points that you encounter, that will become the height of the red curve. If you draw a line in the other direction and count all the points that you encounter, that will be the height of the blue curve, right? So those will be the what is called marginal distribution of X and Y. I will just come to that in a bit. Okay, so that's our next topic, marginal probability of one variable. So let's say between height and weight, I want to eliminate height. Okay, and I want to only look at the distribution of the weight. I only want to look at P of X. So basically, I will take P of XY and I will integrate it with respect to Y. So basically, I will eliminate Y and I will get P of X. Okay, so that's the definition of marginal distribution. So now I get a probability distribution for only the, if I eliminate the height, I get the single variable distribution for only the weight, and vice versa. If I had integrated with respect to dx, then I would have gotten py. Okay, so what that means is you are taking a slice and then you are projecting everything on that slice. So basically, you are counting everything. You're taking a weighted average on that slice. That slice of x. Okay. Then there is something called conditional distribution. Okay, so in conditional distribution, basically you fix the other value. So let's say if I fix the height to be 2 meters or 1.5 meters, then what is the distribution of x? So the way to write it is that p of x, a vertical line means given, p of x given y is equal to 1.5 meters. So it should be the other way around. I think it should be capital Y on this side. So P of X given Y is equal to some particular value. So the way that is done is basically you take, uh, so there's Bayes theorem that helps you with that. You basically take P of XY and you divide it by P of Y, then you will get P of X given Y. So with that we have not shown here, but that's basically the conditional distribution. Conditioned upon a particular value of Y, what is the distribution of X? And that distribution will integrate to 1 also. So that is basically one slice of Y. What does the distribution along the x-axis direction looks like if I take a slice for a particular value of Y? Okay. So when are two distributions independent, two variables independent? When their joint probability can be factorized into their individual probabilities. So in general, P of XY is not equal to P of X times P of Y. Okay, P of XY is equal to P of X and P of Y only if and only if the two variables are independent of each other. So for example, let's say, what is independent of what? Um, you can think of, let's say my voice and my height are, the pitch of my voice and my height are independent of each other, or of people's height. So we are talking about a sample. So the pitch of a person's high voice and their height are independent of each other. Perhaps, I'm not sure, I'm just making it up. Okay. Right, so that's the only condition, that the true test that there is of independence. There is, you can also a weak test of independence is that the two variables are uncorrelated, but the uncorrelation, those being uncorrelated does not mean that they are independent, but two variables being independent means that it is, they are also uncorrelated, but not the other way around. Okay. The next important concept is identically independently distributed sample. All right. So let's say I conduct I do multiple tosses of a coin. So every outcome, let's say if I do it 10 times, so I get 10 different outcomes. Each the probability of each outcome, the probability distribution of each outcome is a Bernoulli variable, and it is same as that of the other toss. Okay, for the using the same coin, but they are also independent of each other. Okay, so then if we look at 10 different coin tosses, they all their outcomes form a independently identically distributed sample. Okay, so heights of two people sampled at random at a metro station are independent of each other, right? Hopefully they are not traveling in families, so hopefully everyone is traveling by themselves for their work. So if you see two random people, their heights are independently identically distributed. Ramohan, what's your question?
Sir, in this, I understand the example of tossing coins because each toss has the same probability of heads or tails, so they can
Right.
be independently identically distributed every toss.
Right.
But sampling two people randomly at a metro station, the probability of their heights will be different, right? How can they be identical?
So that is because we assume that their height, both their heights are distributed as per the distribution of that city's heights. Okay. So both are at 1.6 meters with a sigma of 0.2 meters.
Okay, sir.
Okay. Questions in the chats? Is this PPT shared for simultaneous viewing? It is not. Perhaps is there a TA free who can share this? What is the example of a pair of variables that are uncorrelated but dependent? So uncorrelated but dependent would be so correlation strictly means that if you look at the scatter plot of x and y, you will be able to draw a line that explains the variance, right? Now let's say instead of let me switch to another here. Okay. So right, so let's say this is your x-axis, let's say this is your y-axis, right? And let's say I have points that are distributed like this. So clearly there's a relation between x and y, right? It's not like a random scatter, right? So they are dependent on each other. If you have a value of x that is here, then y can either be this value or this value, but you cannot draw a line, any line that explains this data. So it is uncorrelated, but it is dependent. Does it make sense? Okay. All right. So why this I.I.D is important is because we are moving towards this likelihood tests. Okay. So what is the likelihood of a single instance of a random variable? That is nothing but P of x. So let's say you have a distribution P of x. So what is this theta? Theta is the parameter. So let's say if you have Gaussian distribution, then the Gaussian distribution is completely described by the mu and sigma. So mu and sigma together form theta. If you have a gamma distribution, then it is completely described by alpha and beta. So alpha and beta will basically be the parameter theta. If you have an exponential distribution, then lambda would completely describe it. So lambda would be theta. So now if you have a P of x defined by a distribution parameterized by theta, a set of variables theta, then the likelihood of uh, observing a single variable is nothing, as per definition, is P theta of x1, right? Now let's look at what happens when you draw a multiple samples. If you draw n different samples, I.I.D samples from this distribution, okay, x1, x2 up to xn, and you treat them as separate random variables, then their joint probability, because they're independent, their joint likelihood is going to be the product of their individual likelihoods. Okay, so this pi notation means product from 1 to n of their individual values, individual likelihoods. Usually it's easier to convert products to sums. So instead of likelihoods, we look at log likelihoods. When we look at log likelihoods, it becomes a, instead of a pi, it becomes a sigma, a sum from 1 to n of log of p of x. Sumit, what's your question?
Sir, can you explain me p theta of capital X1?
So,
Capital.
so p theta would be just that formula that you have for a distribution, and you plug in the value x1. That's it.
Sir, just clarify this. Small x1 are individual values like height values.
Yeah.
But capital X1 is the distribution, the random variable. So it may be the distribution of height.
Yeah. So I think I abuse the notation a bit. Here I'm using x1 as the small x1 as the variable and capital X1 as the particular values. I think it should have been exchanged. So that maybe that is causing the confusion.
So sir, how do we, so likelihood and probability, how do we differentiate that?
So probability is finite, right? So that's for intervals,
okay,
or for discrete variables. Likelihoods are for single values.
A single value, like
yeah,
what will be the likelihood of a random person sampled at a metro station to be 1.5?
Yes. So, but if you, even if you take a sample, if you take n different samples of a continuous distribution and you multiply all the likelihoods together, it is still a likelihood.
Okay.
We convert this product to sum because the products very quickly become very close to zero, and it's difficult to deal with them mathematically. So we make them into sum by taking the log. Ram Mohan?
Sir, is likelihood in any way related to expectation or mean or the probability of an event?
Yeah. Of course, it is very likelihood is the we don't call probability of a single value in continuous variables. We just look at likelihoods, right?
So the probability of an interval is same as the likelihood of an interval?
No. So probability of an interval is the integration of the likelihoods of all the values in that interval.
Okay, so do we have a specific value for likelihood of one value of a continuous variable?
Yeah. So that is the value of the PDF.
Okay.
That is same as the value of the PDF. Neha?
So here we're trying to find the likelihood of an I.I.D sample, right? So is the third statement a typo? The likelihood of parameter theta given observations?
So basically what we want to say is that, so let's say if we were to compare two different, so let's say we were only observing samples, right?
Mm-hmm.
Now this sample could have been generated by two different Gaussian distributions and their means are unknown, right? So let's say there are two different Gaussian distributions, one with mean mu1, the other with mean mu2. Okay, so we are looking at, let's say, the first one with mean mu1. So we want to see how likely is it that this sample of n different these n different samples were generated because of mean mu1.
Okay, so but they're independent, right?
What is independent?
I mean, the samples from different distributions, they're all independent of each other.
They're independent, but they're from the same distribution. That's because they're I.I.D. There are two I's, right? So one is independence, the other is identical.
So does that mean that the samples from different distributions would be dependent on the mu1?
They will be dependent on mu1, but not on each other.
Okay.
Yeah.
Thank you.
Ram Mohan?
Sir, can we say like this, because this also seems like a case of conditional probability, that given that the sample is this specific, what is the probability that it came from this distribution?
Yeah, absolutely. That's basically what it is. We are trying to find out what is the likelihood of a particular parameter theta given these n samples. That's exactly what it is.
So given the sample, probability of theta?
it's not probability again, right? Because it's again, theta is also continuous, right? Your mu of a Gaussian random variable can be a continuous variable itself. You can have a mu of 1.5, 1.5001, etc., etc., right? So even theta is a continuous distribution, a continuous variable. So again, we are only talking about likelihood of theta, not probability of theta.
Okay, sir.
Okay. All right. So now if we have two different values of theta, right? So let's look at this example, right? So let's say you have a choice of 3 different Gaussians and you have 10 different samples. Which of these Gaussians, which means which of these mu's and sigmas, right? So theta 1, theta 2, theta 3, right? So theta 1 defines the green curve, theta 2 defines the blue curve, theta 3 defines the red curve. Which of these has the higher likelihood or log likelihood? So let me switch back to this thing. So let's say you have uh, let me get my pen. Right. So let's say you have the x axis, right? And you got lots of samples. Right? And this particular value is around 2, right? This is 2, this is, let's say, 3, right? This is, let's say, 1, this is, let's say, 0, etc. Okay. So these are the balls that you see are the few samples that you got, right? So now if I want to fit a Gaussian on top of this, right, I will have to make a choice between some Gaussians, right? So there could be a Gaussian like this, okay, or there could be a Gaussian that could be somewhere else. Between these two, the blue one looks more likely, but let's say I also had a third choice, right? I had a choice of this one, right? So now between the purple one and the blue one, which one is more likely, right? So these are some of the decisions that we need to make. So the one where the product of all the likelihoods of the samples given so you have 3 different thetas, right? So you have theta 1, you have theta 2, and you have this one is from theta 3, right? What is theta 1? It is some mu and sigma. Theta 2 is another mu and sigma, and theta 3 is mu 3 and sigma 3. Okay, so the one that gives you the highest product of all the likelihoods of the points of the samples will be the one that is the most preferred one, right? So that one maximizes the likelihood. So a lot of machine learning techniques are based on maximizing the likelihood. Okay, and a lot of statistical tests are basically comparing two different distributions, which distribution is more likely to explain the data. That is the whole principle of statistical tests. So that's why we want to cover this here. Okay, questions? Could you answer my question? I didn't get it. X is a possible random value. Okay, all right. Anyone has raised hands? Ashish?
So basically the goal of maximizing the log likelihood is to find a distribution which covers all the points the best, right? That's what intuitively it means.
Yes, yes. That's why you take the product of everything.
Yes,
Okay.
thank you.
Yeah. So there are some questions from YouTube. Goranga has asked, with higher lambda, is it reaching less uncertainty? I think he's talking about exponential distributions. I guess, yeah. So with higher lambda, there is less uncertainty. It's more concentrated towards 0. Then more lambda you have, more you are shifting to the right. No, it's the other way around. You are shifting less to the right. Okay, let's come back to Zoom. Neeraj, what's your question?
So, sir, when you are telling that you are trying to cover the maximum likelihood of the data, so maximum distributions you are
Yeah.
trying to cover, right? So, but maximum
Yeah.
distribution, when we try to cover in machine learning, it mostly goes for overfitting, right? So, I mean, how are we? So, I mean, is it like the right procedure to do that, or I mean, I'm a bit confused in that. So can you explain?
Yeah. So that, yeah. So there are two different things, right? So what is the best distribution that covers a given sample? it's not a Gaussian which has the same mu and sigma as the sample mu and sigma, right? So I could have, for example, let's take another example, right? So let's say this is your, right? So let's say this is your x-axis, right? Let's say you get samples like this. No sample to the left of this. Now, if I fit a Gaussian to this, right, that Gaussian would come somewhere here. Whereas this is not a Gaussian distribution, it is probably a gamma distribution or an exponential distribution, right? So when you force fit a Gaussian, even if you find the best mu and the sigma, note this down, right? When you force fit a Gaussian, even if you find the best mu and sigma for Gaussians, that doesn't mean you have found the best uh, distribution. That just means you have found the best Gaussian, and your assumption that it is a Gaussian could be wrong. Okay, so maybe you should have fit a gamma distribution or an exponential distribution or a variable distribution, right? So it all depends on what is the underlying phenomena that gave rise to that particular sample. Okay, so that's number one. So the best distribution that will fit any set of samples is a distribution that will basically have impulses at each sample, and they all basically will give you a CDF that adds up to 1 with step function. That is overfitting. Okay, if you assume a Gaussian, it's already smoothing these uh, impulses out, so it is doing some sort of something called regularization. So I'm jumping ahead to machine learning. We'll come back to it when we get to machine learning. Arindam?
Sir, actually, I had a question that like you just said, is between two, like optimizing likelihood would optimize our would fit the data points better. Is and there is and the statement that you gave has intuitively a common sense, but my question is that why should we maximize or optimize likelihood on that that specific expression and not some other form of some other product of the probabilities? Why exactly that expression? Is there some proof in that?
So the reason is that it's based in our assumptions itself. We assume that we want to maximize the probability. Right?
Yeah,
so that is,
we assume that we.
And we don't have a better tool
Yeah,
than
but,
probability to look at it. I mean, it's possible there
yeah,
is
but
better form of mathematics to look at it, but we don't have it.
yeah, we're maximizing the probabilities at the multiplication
Or
of
sorry, likelihood.
probabilities,
Yeah.
right?
Yeah.
Yeah. So how are we sure that that is it's optimizing that product is actually the optimum way to optimize our model? How are how are we sure?
It's a little hard to hear. Your audio is quite poor. So maybe we can you can write, maybe you can write it in campus wire and tag me. Okay. Okay, thanks. All right. So maximum likelihood. So basically statistics, the statistical tests are all about looking at one parametric distribution and another parametric distribution and finding out which of the two is more likely to explain the data. Okay. And uh, uh, usually it is some most of the times it is parametric distribution. Sometimes it can also be non-parametric test. We'll quickly cover one of those. uh, in machine learning, you take this theta, the parameter itself as a continuous variable, and you maximize its likelihood using an optimization routine, and then it becomes a machine learning technique of some sort. Okay, so I'll not go into much more detail. Let's quickly jump ahead. Okay. So then there's a concept of sufficient statistics. What that means is that there are some distributions, not all distributions, There are some distributions, if you measure one particular statistic about that distribution, by statistic mean either sum or variance or something along those lines, uh, you know everything about that distribution. You cannot know anything more about that distribution by measuring anything else. So for example, if you have an exponential distribution, all you need to do is either measure the variance or the mean, and you will get a good estimate for lambda, and there's nothing more you need to know. If you have a Gaussian distribution, you will measure the location and the dispersion, which is mean and the variance, and that's it. You don't need anything else. If you have a beta distribution, then mean and the variance may or may not be enough. Maybe you'll need to, or like for some other distributions, you may need to measure some more things to get a good idea. Okay, so only for some distributions, measuring a few different quantities is sufficient to know everything about the distributions and make my maximum likelihood estimates about those distributions. Okay, so in what is central to a lot of statistics is this idea of hypothesis testing. So hypothesis testing means that you have to have two different hypotheses. So let's say I suddenly suspect that people in my class are more intelligent than me. Okay, or let's take a better example. I suddenly suspect that the soap that I buy, they say it is 300 grams, but it is not 300 grams. It is more than, or sorry, less than 300 grams. Okay, so how will I test that hypothesis? I can take 50 different soaps, measure their weight, and let's say they their average comes out to be less than 300 grams. Okay, now it's possible, obviously not every soap will be exactly 300 grams. It will be plus or minus something, because it's no process in the world is exact, right? And it is possible that I got very unlucky, and the 50 soaps that I picked to measure, they all were less than, or their average was less than 300 grams. Okay, so what is the probability that I got unlucky by chance, versus what is the probability that no, really this company is selling soaps for less than 300 grams, but calling it 300 grams, right? So that is what I can do. I can test that using hypothesis testing. So I have two different hypotheses. The first is the one that I want to test, which is that the soap is actually less than 300 grams. And then there's something called H0, which is a null hypothesis. That means innocent until proven guilty, which means that the soap is actually 300 grams. Okay, the average soap is 300 grams. Okay, so we formulate a hypothesis. It's actually two hypotheses: a null hypothesis and the one that you actually want to answer that question. And then you collect the data. Then you will test the two hypotheses and see what is the probability of the null hypothesis. If it is less than, let's say, 0.5 or 0.1, then you can reject the null hypothesis and you can accept the new hypothesis that the soaps are really less than 300 grams. So that is the drawing conclusion part. So that is in a nutshell the entire statistical hypothesis testing. Manan, what's your question?
Is it similar to regression?
No. So regression is a relation between two variables, or one variable and multiple other variables. Okay, so that's basically what you look at once you start looking at scatter plots. You have y versus x. So the relation y expressed as a linear combination of x and a constant, that is a regression. Okay, so here it is not a regression. Here we are saying that if I weighed 50 soaps and their average turned out to be 280 grams and their standard deviation turned out to be let's say 30 grams, then what is the chance that that I got unlucky and I got these numbers, as opposed to truly the company is trying to sell soaps for less than 2 or 300 grams. Okay, so I want to compare these two hypotheses. Okay, so null hypothesis is very important. That is the innocent, like the current state of the world. Alternate hypothesis is the one that is the one that I want to establish, that I want to test. Okay, then you decide a level of significance, which is called a p-value. That means the probability that the null hypothesis is still true Okay. So if it is less than 1% or less than 5%, then you can reject the null hypothesis, and then you can accept the alternate hypothesis. And then you can look at different types of hypotheses: one-tailed, two-tailed, and so forth. One-tailed means that the soap is less than 300 grams. Two-tailed means that it is not 300 grams. It is like either less or more than 300 grams. Okay. Uh, and then, I encourage you guys to look at hypothesis testing. There will be some question, I think, in the assignment based on that. I want to quickly wrap this up because we are taking a lot of time. Then there are a couple of other interesting tests that you should know about. One is called student t-test. It is basically, let's say you have two different samples or one sample. Usually it's used for two samples. It can also be used for one sample. Both come from Gaussian distributions. You want to see whether they're statistically significantly different. So for example, let's say I take height of all boys from Odisha and height of all boys from West Bengal. So are the means of these two significantly different? So if I take 50 boys from Odisha, 50 boys from West Bengal, I get their means, I get their standard deviations. Obviously their means and standard deviation will be slightly different from each other, but how much of it is because of chance and how much of it is because of or are they really truly different? So you can imagine if the, let me go back here. Okay, so let's say I have two different distributions. Okay, I have a distribution like this, and then I have another distribution that is like this, right? So this is the difference of their means. Okay, but what also matters is that it's not just the same difference of means, it's also their variances. If the variances are too large, then it's possible that this difference of the means is not too bad. Okay, because the variance is too large, so there's uncertainty is more. Here the uncertainty is less, so the difference in the means is more significant, even though the difference is exactly the same. Okay, so this is what t-test helps you do. And the formula for that is, let's say if you have two samples and you want to establish that their means are different, you would take the difference of their you look at the difference of their means, and you will divide it by something called S, which basically takes the standard deviation of the 2 points and the number of samples in the in the two samples. So number of boys from Odisha that I measured, number of boys from West Bengal that I measured. Okay. Similarly, if you want to compare two different distributions, if they are different, there is also a non-parametric test where you don't non-parametric versus parametric means. So in parametric test, I assume that the two distributions are Gaussian and there are some parameters associated with it, which is mu and sigma. What if I don't want to assume any parameters? Then I can do something called a non-parametric test, such as a Wilcoxon rank test. So there are several other tests. I won't be covering that, which I want you to start thinking about it when you come across these terms, right? When you want to establish some statistics. So Wilcoxon rank test would work something like this. So let's say I measured all the heights. So this is again, x-axis is the heights, right? So this is the heights, and these are all the heights that I measured for kids from West Bengal. Okay, and then these are the heights that I measured for, let me change the pen color, for kids from Odisha. Okay, so now if I look at their ranks, I rank order them, and I take the sum of all the ranks. How much is that sum of ranks different from the expected value of sum of ranks if they were truly from the same distribution? So that is what is measured by Wilcoxon rank test. And then based on the sum of ranks and then dividing it by the number of samples, you can test it against a table, and that will tell you whether it is statistically significantly different or not. Okay. So that's it. That's pretty much what I have. And then I will hand it over to Path to cover the other portion. So let's look at some questions. Ram Mohan.
Sir.
Yeah.
Yes, sir.
Let me quickly answer Abhilash's question. What's a rank? You basically look at the order from right to left or left to right. That is rank. Okay. Go ahead, Ram Mohan.
So can I ask the question through
Yeah.
of the lecture, or should I just focus on right now? Are you just taking questions for the last?
Yeah. Past lectures I prefer, let's take it in campus where you can tag me there.
Sir, not past lectures, like this lecture, but past slides.
Yeah, tell me.
So can you go to slide number 32?
Slide number.
Likelihood of an I.I.D sample, sir.
Tell me which one. This one?
Yes, sir. So, sir, the previous one.
Okay.
Where there's a formula. Yeah, yes, sir, this one. So I understand why we are multiplying the probabilities, because they are independent. From that formula,
yes.
When we convert to the log formula, first of all, what is the intuition behind converting into the log formula? And is this the same thing that we are calculating?
Yeah, so basically it's the same thing, right? So there is a one-to-one correspondence between the log formula and the previous line. Log is a non-decreasing, it's a increasing function, right? So there's a one-to-one mapping bit. So if you maximize one, you are also maximizing the other.
So both the things are likelihood of an I.I.D sample?
The one is log likelihood, the other is likelihood. The first one is likelihood, the second one is log likelihood.
Sir, is there a reason why we went from the product of the to sum?
Yes. So what we'll do is, when we maximize the likelihood, we will differentiate this with respect to theta, and differentiating a sum is much easier than differentiating a product. Hello?
Yes, sir. So, but like product, we differentiate by the product differentiating product chain rule, right?
Yeah,
okay.
Chain rule, but then you have like n different terms in the product. Here you have n different terms in the sum, which is much easier. And then your P of X, right? P of X, when it takes an exponential family distribution, which means exponential distribution or Gaussian distribution or couple of other which have a particular form, mathematical form, taking log makes it much simpler. It's a mathematical simplification.
Okay.
No theoretical basis. It's a convenience basis. Where will we use hypothesis testing in any ML methods? In ML methods, we may not use, but we will maximize the likelihood. So hypothesis testing is comparing likelihoods in some sense. Okay. But comparing likelihoods of only two different hypotheses. If we convert the entire space of hypothesis into a continuous space by parameterizing it with theta, and we find the solution to that continuous space by differentiating and setting the derivative to 0, that becomes an ML problem. That becomes a more optimization based problem. So ML is in some sense statistics on steroids. So you lose some rigor, but you gain on things you can do with ML, but its basis is in statistics. Ashish?
Sir, my question is centered around the fact that if you talk about the application of hypothesis testing, like these raw tests, like Wilcoxon test and all these things, so how do they fit in our problem solving pipeline, or do they fit like in their rawest form, in their purest form, or they don't? What's your opinion on it?
Yeah, so they have two different utilities, right? One, they are used in their raw form. So raw form means, let's say you invented a drug to cure Alzheimer's, right? And you gave it to 1,000 patients and 200 of them were cured. Okay. Is that a random fluke, or is your drug really effective compared to giving them a placebo? Placebo means sugar pill, telling them that you are giving medicine, but you are actually not giving them medicine. That's how these tests are conducted. Medicinal tests are conducted, right? Because there's a little bit of faith healing with placebo. You think you are getting better, so you might get better. So you take two different samples. One has 500 people, the other has 1,000 people. You give one of them placebo, you give the other one your drug. Okay. And they are exactly the same type of population, same age group, same gender mix, etc. Okay. And now you look at how many people got cured by just taking placebo, which is a sugar pill, and how many people got cured, or what percent of people got cured by taking your medicine. And then you compare the null hypothesis that your medicine is not effective versus the alternate hypothesis that your medicine is effective. If your null hypothesis has a very low probability, that means your medicine is, you can assume with good confidence that your medicine is effective.
So sir, basically it's something like,
use of it.
So basically it's something like it is good for small sample sizes.
It's also good for large sample sizes.
like these tests are good for large, like of course for large it will be good, but for that we might have some ML methods and all those things to do also, right? I mean,
No, you just want to see whether you can claim something or not. And if you
okay.
claim it,
Okay.
what is what is the what is the basis, what is the scientific basis, or what is the statistical basis for your claim?
Okay, yeah, okay. Thank you, sir.
Okay. So let's say, is there power in prayer? I'm going into a controversial subject, right? We and we are afraid to test it for various reasons. But let's say, we were to one day test that, right? So perhaps there is, perhaps it like focuses your mind and it actually does something for you, right? So, but you could test it, but we don't. So, but we do that test every time whenever there's a medicine that is released in the market. Before it is released in the market, we do multiple tests on multiple samples. Okay. All right. The second use of this is that once you have an ML technique and it is giving you good answers on a particular data set, what is the guarantee that it is not by fluke? So you can now use a statistical test to compare your technique against a previously existing technique. Okay. So that's when you will show it and you will get that you can show that there's statistical basis for you to claim that your technique is better than the other technique. Usually people just show the average result and they are done with it. But a more stronger result in a paper would be that you actually show that it's not just the average result that is better, but you also are looking at the variance, and based on that you have constructed a statistical test like a t-test or something, and based on that, or Wilcoxon rank test, and based on that you can claim that your technique is better than the technique that came last year. Okay. Ramohan?
Yes, sir. Sir, coming back to your example of the soaps,
Question?
where you said like we are taking we are measuring weights of soaps, 30 samples. We took 30 samples, and we are considering whether the weight is less than 300 or not.
Yeah.
So, sir, and we want to see, let's say for all the 30 samples, we got weight which is less than 30, and we want to figure out if this was by chance or not. So, sir, until we have more samples, how can we figure this out with just this sample, that whether this was by chance or not? I am not able to imagine that, sir.
I mean, you can only say that there is 5% or 7% or 10% probability that you got a lower weighting sample by chance. That's all you can say. You can never say with 100% certainty.
So, sir, I'm saying, how can we see this 5% until we know? We can maybe say this 5% when we know the production of the company and we have some data of that company, like what was the weight that they were producing. But given just the samples, how can we say it's like 5% we got?
Yeah, I mean, you can, right? I mean, you basically, let's say your average of the 30 soaps was 280 grams.
Yes, sir.
Okay. And let's say if it was 299 grams and the standard deviation was 5 grams.
Yes.
Okay. Versus it was 290 grams and the standard deviation was 5 grams. When will you be more confident that they are producing a lighter soap?
The 291, sir. That would be the right.
So yeah. So there is actually a statistical test that will tell you which one is more probable.
Okay, sir.
In which case the null hypothesis is more probable. Okay, that's what we mean by this. All right. San?
Hello, am I audible?
Yes.
So in one of the previous slides, you said that we try to fit multiple distributions to a particular sample. But if we use the central limit theorem and just have multiple samples, they all follow the normal distribution. So why try to fit a particular sample to a distribution, to a particular...
They don't follow the normal distribution. No, they don't follow normal distribution. Like heights of people cannot be normal, right? Normal is extend minus infinity to plus infinity, right?
Okay.
So heights is never negative.
Yeah.
Right. So normal is not always the right answer.
Okay.
So you can actually fit different shape distributions. Okay. Abhilash, can hypothesis testing be used to show the confidence in the model's accuracy score? Yes, you can do that. So let's say you did, you looked at segmentation output of your neural network, right? And you're looking at a metric called intersection over union, and average intersection over union is around 0.8, but then the standard deviation is also very small. That means you have high confidence that it will be 0.8 on a new sample also, right? So you can do statistical testing on that, but most people in ML is so fast paced that people are not very rigorous with statistics in ML. But you can be more they are more there. You can be more rigorous about statistics in ML also. People want to do more complex things without being rigorous in ML. Let me put it that way. Okay. All right. Any other questions? Okay, so that's pretty much it. Now we will release the assignment. It will be based on these things. So basically, you just have to look at these formulas, search them on the net, some of the ones that are not covered, and just program it in Python and do the assignment. So there will be things like calculate the likelihood of something, calculate the um, probability of something, and so forth. Right. So you will get that assignment shortly. So Jay, you have a question?
Sir, can we in upcoming module of ML can we have assignments like this that code logistic or linear regression from scratch, make your own functions? Can we have assignments like that?
Yeah, we can do that. We can do that. Yeah. Okay.
Because like many people and even I am like familiar with using functions, built-in functions and using it.
Right.
It's not a challenge. The main challenge is to understand it to the core. So we have to, when we will make our own function, then we will understand it properly.
Yes. Okay.
Yeah,
We'll keep
humble
that in mind.
request.
So we will start with black box just using functions, so that first you get an overview, and then we will delve deep into some of the models. Okay. We'll take the reverse approach in some sense. All right. Ramohan?
Sir, if you have time, if you can answer just one question, sir. I'm still not being able to being comfortable with the likelihood meaning of the likelihood in general practical sense, sir. Can you explain it with an example, please?
Likelihood is nothing but the height of the PDF at a particular point. Okay. So because for continuous distribution, there's no probability of a particular point. It's only the likelihood of that point. So let's go back to another example, right? So let's look at a sample. Okay. Let's look at a sample now, right? So let's say you sampled heights of people, right? Right. This is like the really tall guy in the class. This is like whatever, right? Okay. So you have this sample now, right? Now I want to find out which mean will explain these. Let's say the variance is fixed, right? The way, let's say I want to find out which mean will explain these points best. Okay. Now for the same X space, in the same X space, I also plot mu space. Okay. So I can choose mu here, I can choose mu here, I can choose mu here, here, right? So if I choose the mu here, then the likelihood that I will get for this particular theta is mu now, right? For this particular theta, I will get some low value of product of all the likelihoods of all the points. For this particular mu, I will get slightly higher. For this one, I will get slightly higher. This one, I'll get lower again, lower again, lower again, right? So this is sort of the curve of likelihood of theta, or likelihood of mu. Okay, the maximum one explains the data best.
So, sir, wouldn't we choose the mu by calculating the mean of every sample, sir?
Yes, you can do that for a Gaussian distribution. If you assume the distribution to be Gaussian, then you can do that. Yes.
Sir, if the distribution is like any other distribution, we can still calculate its mean, right?
You
Like
can
to make it,
calculate its mean.
I mean, expected, like weighted mean.
You can not weighted mean, again you will just calculate mean in that case. So when you have samples, then there's no weighted mean, it's just mean. Weighted mean is when you have a continuous distribution or a probability mass function.
Yes, sir. So I'm
Sumit, but go ahead, Ramon.
so I'm trying to understand, like, why do we have the vertical lines that you were drawing for different values of means? So which one would be better or not? We would, like, instead of comparing all these values, we would just calculate the exact absolute value of mean.
Yes, you will do that for simple distributions like Gaussian. But in ML will come to distributions where it will not be obvious.
Okay, sir.
In ML, we can use distributions that are mixture of Gaussian. It's a bimodal distribution or trimodal distribution.
Okay, sir.
Okay, so then it's not obvious. I need to calculate 3 different means. I need to calculate their heights. I need to calculate their sigmas, right? So I need to estimate 6 different parameters. Then it's the maximum likelihood estimate is not that obvious.
So these are different variables or parameters, sir?
This is the entire distribution that I'm modeling, where I can, which is controlled by 6 different parameters.
Okay,
This
so
lambda 1, lambda 2, lambda 3, and
those.
then mu1, mu2, mu3, and then sigma 1, sigma 2, sigma 3.
Okay,
So in ML, we'll deal with more complicated distributions.
Yes.
Okay, Sumit.
Yeah, sir. So I got most part of this explanation. Only thing that the likelihood of mu, the curve which you drew, mathematically how you calculate it, multiplying mu with what, sir?
You're not multiplying mu. You are computing the likelihood of all the samples given that mu.
Okay.
You are computing the and their product or the sum of their logs, either sum of their logs or the product of their likelihoods, right? And then you're doing it again at this point. You are doing it again. So you're doing it at mu1, at mu2, mu3, etc. And the mu that gives you the highest likelihood is the best answer. In actuality, you will actually be doing it over a space of not just mu, you will be doing it over a space of mu and sigma. So this will be your mu space, this will be your sigma space. And uh, for a particular mu and sigma, you will get some particular value coming out of this plane that will tell you what is the likelihood of the data, the I.I.D sample, given this value of mu and sigma, this pair. So the one that gives you the maximum value, so let's say these are contours now, the one that will give you the maximum value of the hill, that will be the value of mu and sigma, that is the best answer. Okay, so that is very easy to do for Gaussian. You just take the sample mu and the sample sigma. That is the concept of sufficient statistics for these special distributions. But these special distributions are not very useful when you are trying to model lot of points and that may be multimodal and so forth. Multimodal means they have more than one mode. They have 2 peaks or something like that, 2 local peaks.
So, sir, just to talk about the application point. So, is this way that we find distribution of some unknown experiment?
No,
Like,
so basically, yeah, we'll make a function of, let's say, theta, or basically a function of mu and sigma, and then we will differentiate it with respect to mu, and then we'll differentiate it with respect to sigma and set those derivatives to 0 to find this central point, because at this point it is flat, the derivatives are 0.
yes, sir. So,
Yes, so that's how we'll do it in ML.
Yeah. So, sir, I was talking about the application point, like suppose the Rayleigh distribution or a Riccian distribution, which we study in wireless communication.
Yeah.
So we found out those distribution using these methods. Like
Yeah.
first we were
So
not aware of the distribution and so
yeah,
forth.
so you assume a Rayleigh distribution with, let's say, whatever number of parameters it has. Now you want to estimate the parameters. Either If Rayleigh has sufficient statistics that will define the parameters, then you use the sufficient statistics. That's an easy answer. If it does not have sufficient statistics, then you will make it an optimization process and set the derivative with respect to the parameters to 0.
Okay.
All right. Let's see, any questions from YouTube? So Arindam, I guess you have asked the question, why do you define likelihood as the product of all probabilities? Because they are independently distributed. Each point we assume to be independent of each other. Right? Okay. All right. So I think I've answered most of the questions. Okay. So then we'll call it a day. I hope you guys learned a lot in this data science module. We'll have one more assignment, and then we will, in 2 days from now, we will jump into the machine learning module. Okay. All right. Thanks a lot.